All right, for the last video in section 15.2, we're going to look at problem number 9, which in part are just some additional exercises in computing line integrals, but it's also a preview of something really important that's going to come up a little bit later in the chapter. Okay, so our job is to compute the work done by the rotation field F, which is equal to minus y comma x. That's that same rotation field we encountered in problem 1. Over the three paths pictured below. And then it says, is this line integral independent of path? Okay, so we're going to integrate this vector field f, this rotation field, over this straight line path, C1, this circular path, C2, and then this piecewise linear path, C3. Okay, so for C1, and now I'm going to kind of just jump ahead, okay, because this is all the same. And in fact, if you want to pause the video and work through these, very good practice just setting up and computing line integrals. But for this straight line path, okay, I parameterize that line segment as 1 minus t for the x coordinate and t for the y coordinate. So if t is 0, I'm just going to be located here at 1, 0. And then as t increases from 0 to 1, I'm moving along this line where x plus y is equal to 1. See if I add these components, I'll just get 1. And when t is equal to 1, then I'm going to be located up here at the point 0, 1. Okay, so here's my derivative vector. Here's my vector field evaluated along the path. And then I just compute the line integral in the usual way. And here I wind up getting a value of 1. Okay, now if I do the integral over the circular path, okay, that's right here. I'm just going to parameterize that as cosine t sine t. So that's this counterclockwise parameterization. T will vary from 0 to pi over 2. And then here's your derivative vector and your field evaluated along the path. I'm going to go ahead and compute that, and I wind up getting a value of pi over 2. Okay, so the work done by this vector field f to move an object, say, from the point 1, 0 to 0, 1, is different along these two paths, C1 and C2. Okay, and furthermore, if I look at this third path, notice I'm going to have to break this up into two pieces. So I parameterize this first piece as just 1 minus t comma 0, because x is decreasing from 1 to 0, and y is just constant 0. And then I have this second piece where I parameterize that as just 0 comma t, because x is constant 0 now, and y ranges from 0 up to 1. Okay, and when you compute that integral, you wind up getting 0. Okay, meaning that the total work done is in fact 0. Now remember, that does not mean that our necessarily that our force and our direction of motion is always perpendicular. Okay, in general, it can be a combination of places where the force is, say, acute, and then where it's also obtuse, and then the combination comes out to be 0. But nonetheless, we can see, right, that for each of these paths, I'm getting a different value for the line integral. So we would call this vector field here, f, okay, as we move an object from the point 1, 0 to 0, 1, this is path dependent. Okay, and now in a little bit later in the chapter, we will see examples of both path dependent and path independent vector fields, and that's going to be related to potential functions. Okay, so some good stuff to come a little bit later. All right, that's going to do it for this section. Thanks so much.